So we're talking about infinite dimensional Fisher-Rao metric and Wasserstein distances. So it's supposed to be following Professor Amari's talk. But anyway, so I wouldn't do it first. So the talk, I will be talking about the generalization of the following geometrical structures for probability measures on in Rn to the including the Fisher-Rao metric and distance, which is a central topic in information geometry and optimal transport distances, to infinite dimensional probability measures. So now the results are on the infinite dimensional Gaussian measures and Gaussian processes. Of course, infinite dimensional probability measures are very highly complex. So just focus on the Gaussian setting. So for this setting, because it's an infinite dimensional setting, so we need to employ many techniques from functional analysis. So it will involve the interplay of the following theory and techniques from various different mathematical fields. So we have operator theory, especially the theory of positive definite operators, which generalizes the theory of positive definite matrices to the infinite dimensional Hilbert space setting. And we will need to employ infinite dimensional Riemannian geometry and Gaussian measures on Hilbert space and Gaussian processes. And the analysis will be for the sample complexity, it will involve RKHS methodology and probability theory on Banach and Hilbert spaces. Okay, so in the finite dimensional setting, we actually have a lot of work on the various geometrical structures of Gaussian measures and symmetric positive definite matrices, or SPD matrices, because they play a central role in probability statistics and machine learning, of course, but there are also a lot of practical applications in many different fields. So we have a lot of applications in brain imaging, in computer vision, in radar signal processing, in brain-computer interfaces. So actually, there's a huge literature of work actually using the non-Euclidean geometrical structures of Gaussian measures and SPD matrices. And in general, it has been demonstrated that they work better, they give better practical performance compared to the Euclidean distances and matrix, even though they are more computationally demanding. So my focus is really on the setting on the Hilbert space. But so let me first review very briefly the Fisher-Rao metric and the corresponding affine invariant Riemannian metric. So let's go to the set of n by n SPD matrices, and we have so it corresponds to the set of Gaussian densities on Rn, zero mean, because they are completely characterized by the covariance matrix, sigma. And so on this, we can define the Fisher. In general, actually, on a set of Gaussian densities parameterized by a set theta, we can define the Fisher information matrix given by this formula here, this formula here. And if this matrix is positive definite, then we will define a Riemannian metric on the set S. And so for the case of Gaussian densities, a set of Gaussian densities, it is positive definite, and it defines a Riemannian metric on S. It's called the Fisher-Rao metric or the Fisher information metric in the literature. So this is actually this is a very old concept in statistics. And so it's a central element in information geometry. So Professor Amari has not arrived yet, but anyway, so for the explicit, so in the Gaussian setting, we have explicit expression for the Fisher-Rao metric. So it's given by this formula here. And since we have the one-to-one correspondence between the set of SPD matrices and the set of Gaussian densities on Rn, so we have the corresponding affine, Riemannian metric on the set of SPD matrices. It's called the affine invariant Riemannian metric. So it's given by this formula here. This is kind of the inner product at the point sigma. So this is like the A and B are in the tangent space at the point of the manifold at the points at the SPD matrix sigma. So A and B are symmetric matrices. The set of symmetric matrices form the tangent space of the SPD matrices. And so this has been studied extensively. Actually, it's very old. So I'm just listing some of the recent references here, but it's actually a very old. It actually studied kind of independently also from the statistical setting. It has at least in the I can just at least as far back as the 1940s actually. So here we have it's called the affine invariant Riemannian metric, and it has a lot of applications. So here, for this metric, we have a unique geodesic joining A and B. Any two matrices A and B, it has a closed form formula, and the geodesic distance has a closed form formula. So there's a lot of, and this one is corresponding to the Fisher-Rao distance between zero mean Gaussian densities on Rn. So it actually has it has been studied extensively in the literature. So my focus is really on the infinite dimensional setting. So we have the generalization of the Frobenius in the product and norm. to the Hilbert space setting is the Hilbert-Schmidt inner product norm. So it's given by, if we write like this kind of the inner product of A and B is given a chess by star B, so it's the same as in the Frobenius inner product, except that we have now infinitely many, we can re-specify in terms of orthonormal basis, and for any orthonormal basis. So it's an infinite sum, and so we have the set of Hilbert-Schmidt operators where the norm is less than infinity, and in the case when the operators are self-adjoint, so it's written by the sim here, it's symmetric or self-adjoint, then this is just given by the sum of all the eigenvalues square. And we also have the set of trace class operators. So these are bounded operators with finite trace norms. It's given by, so if, and for A in this set of trace class, then the trace is just given by this formula here. So if A is a self-adjoint, then the trace norm just is the summation of all the absolute value of all the eigenvalue, and then the trace is the summation of all the eigenvalue. So this one is like an L1 norm, and this Hilbert-Schmidt norm here is the L2 norm. And so in the case when H is infinite dimensional, of course, it's the set of chess class. It's a strict chess class operators. It's a strict subset of the set of Hilbert-Schmidt operators. We actually will be using both of these sets of operators later on, but we actually need to extend them for our purposes. So we are going from the finite to the infinite dimensional setting. So on our end, we have a Gaussian measure here. With I'm just talking about the case with zero mean. So we have mean zero and covariance matrix C. So in clean space, we have Gaussian measures corresponding to a set of semi-definite matrices. And for non-degenerate Gaussian measures, so that they have a density, then it corresponds to a set of symmetric positive definite matrices. Everything is strictly positive. And we have the similar thing on Hilbert space. So we have the Gaussian measure correspond to a set of positive trace class operator, and for the non-degenerate Gaussian measure, then we have the set of strictly positive trace class operators. So this set is, so we have, when we study the correspondence between Gaussian, we have the correspondence between Gaussian measures and positive trace class operators. So we have the geometry of Gaussian measures basically correspond to geometry of positive trace class operators. But for the, if we want to generalize the Riemannian metric, it's actually necessity because of the larger set of positive Hilbert-Schmidt operators. So in the finite dimensional setting, of course, they are the same. The norms are all equivalent, so they are the same. But in the infinite dimensional setting, the classes of operators are different. And this class is the positive Hilbert-Schmidt operators is larger, strictly larger. And it can be, it has been, there's an extensive literature in mathematics actually on this, the geometry of positive Hilbert-Schmidt operators, and they studied independently of the probability and statistics settings. So what I'm going to talk about is actually kind of the connection between this purely geometrical setting of positive Hilbert-Schmidt operators and the probability and statistical theory of the Fisher-Rao metric. Yes, please. Positive, yeah. And then plus is strictly positive. Yeah, positive semi-definite. Yeah, but I think call it positive in kind of the definition is actually positive and strictly positive. Yeah, that's one way to do it. Yes. Yeah. But I'm just talking about the case when the mean is equal to 0 to simplify everything. But yeah, actually that's one way to do it. The embedding, yes. So now let's consider the case we want to generalize. Let's talk about the generalization of the affine invariant Riemannian metric from the set of SPD matrices to the infinite dimensional setting. So let's suppose that A is a strictly positive Hilbert-Schmidt operator. So we have a set of eigenvalues. So they're all greater than 0, and so we have a spectral decomposition given by this formula here as a stability singular value decomposition in finite dimensional. The problem in the infinite dimensional setting is actually we have, because the eigenvalues go to 0, and so the A inverse will be unbounded. And the log A is also unbounded because it's go to the log lambda can go to negative infinity. So these operators are unbounded. And if we have the expression of A as in the geodesic distance, so with this expression here is generally unbounded. It can be bounded, but only under certain assumptions, which I will show later on. But in general, it's unbounded. So one way to overcome this is to do regularization. So in mathematics, it's called unitization. So we consider operators that form A plus, instead of just A, we consider A plus gamma I, where gamma is greater than 0. So then all these operators are bounded. Remember that A is positive. So these operators are bounded. And so we can, so this log is also unbounded. But the problem is actually, if we just use the Hilbert-Schmidt norm, then this quantity is actually generally infinite when gamma I is not equal to mu. This is because the identity operator is not Hilbert-Schmidt, so the Hilbert-Schmidt now the identity operator is equal to infinity. So what we need to do is, so the solution is actually proposed a long time ago. It's the extended of the unitized Hilbert-Schmidt operator. So instead of consider just the A Hilbert-Schmidt, we consider the set of A plus gamma I, where A is Hilbert-Schmidt. And it's necessary to introduce the, to include the identity operator as well, to enlarge the set of Hilbert-Schmidt operators to include the identity operator. So we can, this one is called the extended Hilbert-Schmidt inner product and extended Hilbert-Schmidt norm. So then we define this inner product here and the norm here, so that the norm of the identity operator is equal to 1 instead of equal to infinity. And then we consider the set of positive unitized Hilbert-Schmidt operators. So of the form A plus gamma I. This is an open subset in the Hilbert space of the Salvage-Choi extended Hilbert-Schmidt operator. So this is infinite dimensional Hilbert manifold. And so then we can define, so everything here, we can define the generalization of the phi invariant Riemann metric. And so this expression is very similar to the finite dimensional setting, except that we add a unit, like an extended operator. We use an extended operator throughout. And so we have, it's actually the kind of the properties of the finite dimensional setting is all carry through. So we have a geodesically complete manifold non-positive sectional curvature. We have a unique geodesic joining every pairs A and B. And we have the Riemann distance have the closed form. So it's actually very similar to the finite dimensional setting, except that we use the regularized or extended or unitized operators, and we use the extended Hilbert-Schmidt norm. So there are two components in this formulation. So that was the work of Larotonda. So now I'm also talking about the connection with the infinite dimensional divergences. We have a lot of different, we have many various, apart from the Riemannian matrix, we also have the divergences. So this is a set of log divergences, a family of parametric divergences correspond to the Riemann divergences between Gaussian densities and Rn. So they define things the log function and the trace. So now these formulas do not generalize directly to the infinite dimensional setting, except in very special cases. And the problem is actually, as I said, that the log A is unbounded, also A inverse is unbounded, so the data is also only well-defined and bounded for the trace only on specific classes of operators. So the approach similar to before is that we use regularization or unitization. It's actually a very similar idea. We just extended the trace, and we generalize as something called the extended the Fredholm determinant, something called the extended Fredholm determinant. So it can be done. It's actually very similar to the idea of the extended Hilbert-Schmidt norm. We don't have to worry about the technical details so much, but we can actually do it. So we have, this is a simplified version, because actually the full version is actually more complex. So we can identify the alpha log net divergence in a very similar way, except that we use the extended operators and we use the extended Fredholm determinant. And so all the quantities are finite and they are valid divergences. We can improve many other properties of the divergences as well. And in the case when alpha is equal to 1, we can show that if we have two equivalent Gaussian measures on Rn, then on Hilbert space H, then when gamma goes to 0, we recover the exact K-on divergence. So this is the kind of the connection between this regularized K-on the regularized log net divergences with the Rene divergences between equivalent Gaussian measures. And with actually a much larger family of divergences called the alpha beta log net divergences. Actually, this is also the work in the finite dimensional setting. Professor Amari actually worked a lot on these divergences. So in the case of positive definite matrices, we have the alpha beta log net divergences. And so we have also the generalization to the infinite dimensional setting. So we also have something called the alpha beta log net divergence for positive definite Hilbert-Schmidt operators. And we use something known as the extended Hilbert gamma determinant. So this is a very general family, and it encompasses both the alpha log net divergence I was talking about just now and the alpha invariant Riemannian distance. So it's actually a very general family of divergences. And it's more general than the Gaussian setting because we're actually talking about positive definite Hilbert-Schmidt operators. So, okay, so now I was just talking about the alpha invariant Riemannian metric and the generalization to the infinite dimensional setting and the log net divergences and the generalization to the infinite dimensional setting. Now, before I was recalled that we have the correspondence between the alpha invariant Riemannian metric and the Fisher-Rao metric for the Gaussian measures, for the Gaussian densities and the SPD matrices. So we are going to do similar things for the generalization of the Fisher-Rao metric. using the pi invariant metric for Hilbert-Schmidt operators, for positive Hilbert-Schmidt operators to define the Fisher-Rao metric. But in this case, it's more complicated. So because in infinite dimensional setting, there are several challenges. So number one, on Rn, we typically work with probability density functions with respect to the Lebesgue measure. So on a Hilbert space or infinite dimensional Banach space, there's no Lebesgue measure, and so we don't have a natural reference measure. So what we can do is we can consider a set of probability measures on H, which is equivalent to a fixed measure mu0. So then with the Radon equilibrium densities d mu 0 is actually it exists and are strictly positive, so we can consider a generalization. So there's been actually many work in the literature in highly abstract settings. So in the work of Pistone and many of his colleagues, we consider like infinite dimensional Banach manifold model on Hawke spaces and probability measures equivalent to a given one, and we have the work of Newton. The Hilbert manifold probability measures of finite entropy equivalent to a given one. So the Fisher-Rao metric in this case is generally a pseudo-Riemannian metric. And we have the setup, a series of work by Ye, Yost, Ley, and Schwarhofer. When we consider like they consider the natural immersion of the set of probability measures into Banach space of all finite sign measure the total variation norm. So this series of papers are highly abstract. What I'm going to talk about is an exclusive focus on the set of equivalent center or zero mean Gaussian measures on Hilbert space. Now, there's a drastic difference between the finite dimensional and infinite dimensional setting on the on Rn and the2 Gaussian densities. They have the same support, like the full support of all of Rn, so they're all equivalent. So equivalent means that they have the same support. In the infinite dimensional setting, we have a classical result of Hellman and Harjek that says that we have two Gaussian measures are either mutually equivalent or they are mutually singular or equivalent. So they have either the same support or the disjoint support. And we have a necessary sufficient condition for the equivalent Gaussian measure. So the mean has to be related by this condition number one here, and the covariance operators have to be related in this form here. So we will actually use this relation of the covariance operators to define for our purposes. So we can only consider the set of all Gaussian measures equivalent to a fixed one, not the set of all Gaussian measures on the Hilbert space. So it's different from the finite dimensional setting. So we just fix a Gaussian mu0. So you cannot degenerate. So then this one has all strictly positive eigenvalues. And we consider the set of all self-adjoint Hilbert-Schmidt operators so that I minus s equal to 0 using this form here. And then we define the set of all Gaussian measures equivalent to mu0. So it's given by this expression here. And so this is actually is an open subset in the Hilbert space of self-adjoint Hilbert-Schmidt operators. So it's a Hilbert manifold. And so this set of Gaussian measures equal to mu0, Gauss H mu0 here is parameterized by this dimensional Hilbert manifold. So now it's a Hilbert manifold, and then we can and then the set of corresponding covariance matrices and covariance operators. So for the case of Gaussian densities, we have the set of SPD matrices for the Gaussian. In this case here, we have the set of this set of operators here. It's a subset of the set of positive stress class operators. So it's given by this formula here. This is C separated by C0 by this formula, as we said for the equivalent Gaussian measures. And we can show that it's actually an open subset in the bigger Hilbert space. So then it's a Hilbert manifold, and so that we can use this for our purposes. So now, okay, I'm gonna actually skip this. So the expression for the Fisher-Rao metric, before that we have the we have the density function we differentiate with respect to different h parameter theta I. So in this case, in the more general setting, we use the Fisher derivative. So first we have the Radon equilibrium densities, and then we compute the Fisher derivative at each point s on the manifold of the parameters, and then v1, v2 here are the tangent vectors at s. So this is the expression for the general expression for the Fisher-Rao metric. So of course this expression is only well defined. Of course, number one, it has to be differentiable, and number two, the Fisher derivative has to be in L2. Otherwise, the expression would just be infinite. And we can compute it kind of in some cases we can compute. So in the case when S is Chess class, for example, we can compute. This is the expression here. Now remember that this operator here is actually unbounded. The C0 inverse is actually unbounded. So this expression is not defined by itself. It's actually defined by a limiting process in L2. So this is the limiting process. Otherwise, this one is actually unbounded. And then in the setting of, this is the case when S is Chess class and B is also Chess class. In that case, we can actually take the limit in L2. Okay, I wouldn't actually go fast because we just I just want to say that we can take the limit. We can take the limit in L2 and to cover everything. But the most important thing is actually we have this expression here, where this is the inner product in L2, and this is between two. We have two tangent vectors here, V and W, and so the expression is given by this formula here. So this gives us the Fisher-Rao metric. Yeah. So this is the Fisher-Rao metric. It's given by this formula here, and it can also be derived here. And for the on the set of covariance operators, we have the corresponding Riemannian metric. So it has the same expression as in the finite dimensional setting. But everything here is well defined. Everything here is bounded. In general, it's not bounded, but everything, in this case, everything is bounded. And so in the finite dimensional setting, we can also write like trace of sigma inverse, sigma A1, and sigma inverse A2. But that expression is generally unbounded, where this expression is always well defined in this setting. And this expression here, so I have just shown that we can use it from the direct definition. We can also define this using the Hessian of the K-on divergence. So we also have the closed form formula for the K-on divergence with the equivalent Gaussian measures on Hilbert space. And okay, so we have 10 more minutes. So we can talk about, okay, so I'm just going to mention that you don't have to worry about the details here. I'm just going to mention that we can compute everything. We can compute many things. We could compute many things. On the Riemannian structures on this manifolds, we can compute the Levi-Civita connection. We can compute the Riemannian curvature tensor. We can compute the sectional curvature. Anything we want. And the expression are basically the generalization of the finite dimensional setting, except that we explicitly use the extended Hilbert-Schmidt operators. So this is actually a crucial component in the formulation. And also we have a geodesic. We have a geodesic curve. It has a similar form to the finite dimensional setting, and we have a geodesic distance. So it's actually, this expression here is well defined. As I said, in general, it's not well defined. In this case, it is well defined. And so what is the connection of this with the Riemannian geometry? Possibly definite Hilbert-Schmidt operators. So one, we were actually using the extended Hilbert-Schmidt operators to formulate the Riemannian manifold structure for the Fisher-Rao metric. We also have this formula here, the kind of the limit of this expression when gamma equal to 0. This is the Riemannian distance, the geodesic distance in the case of the affine invariant Riemannian metric. And if gamma equal to 0, then we just obtain the Fisher-Rao distance. So so we have a very close connection between the two formulations, as in the case of the finite dimensional setting. Of course, in the infinite dimensional setting is technically a lot more involved. So, okay, so with the abstract setting, okay, in the Riemann, okay, I don't think I'm going to have time to talk about the optimal transfer, but just talk about the Gaussian process setting. So we have a concrete setting now for the Gaussian process. So we consider the Gaussian process with mean function m and covariance function k. So assume that the sum of parts belong to L2 to T, where T is like a compact metric space for some interval from 0 to 1, and we have a nice measure, for example, on T. And so in this case, we have the the sum of parts of the Gaussian process belong to L2 if and only if the mean function is square integrable, and then we have this condition here for the covariance function. So we have a one-to-one correspondence between measurable Gaussian processes and Gaussian measures. So the mean is the same, the covariance Gaussian measures of the Hilbert space H to L2 T nu. So this is the Hilbert space in this case. So it's a concrete Hilbert space, and the covariance operator is given by just the integral operator with the kernel KST. So you can imagine that we will actually have the RKHS formulation in RKHS methodology into the picture very soon, because we have the kernel with the covariance function being a kernel. And so, for example, these are the examples of two Gaussian processes, and we can. So actually, there's a lot of work in studying the divergences in this Gaussian process. It's the literature. So a lot of work in functional data analysis focusing on the Hilbert-Schmidt distance. And we have the, this also work on the Wasserstein distance and the KM divergence. Okay, I'm gonna skip this. So we can show that, so before we have the kind of infinite dimensional setting, in general, we cannot really compute the infinite dimensional setting. In general, it's actually very difficult. So what we can do is we can do the estimation of the infinite dimensional formula. In this case, in L2, we have the distance or divergence between two Gaussian measures on this L2. And using the finite dimensional formula in RM, we see here we can sample like n points on the set T, and then we have the corresponding gram matrices. And so these vectors here is actually distributed according to Gaussian distributions with covariance matrix Ki. This is the definition of Gaussian processes. And so we can do this estimation. And this analysis here actually makes sense if you use the RKHS operators. So I'm going to show you the formulas here that we can estimate the infinite dimensional distance by the finite dimensional distance, and we have like a dimension independent sample complexity. I mean, we can also estimate from finite samples as well, but I'm going to skip this. Or maybe I still have time for the optimal transport. I will talk very briefly about the optimal transport. So, for a comparison, we have the optimal transport here. So Marco Couturi was talking about the optimal transport yesterday. So I'm just talking about the case when we have the two loss functions. So then we compute on the inverse space setting, and we compute the entropic regularization at the term with the mutual information between the joint measure gamma and mu0 and mu. So we have something called the Synaptic divergence. So for the Wasserstein distance, we have a closed form formula. So it's actually very different from the Quang divergence of the Fisher-Rao distance, because in this case, everything, the distance is actually the same as exactly the same as in the finite dimensional setting, and we don't have to worry about Gaussian densities here, because everything is well defined, even if the Gaussian measures are singular. So this is a very strong advantage of the optimal transport setting, and has been applied to Gaussian processes as well. So SSR is actually valid for the singular covariance operators. One difference is actually, one thing is not so desirable, it's actually not Fisher differentiable. And we also have a closed form formula for the synchron divergence between Gaussian measures on Hilbert space. Marco Couturi and his colleagues have worked out the formulation for the finite dimensional setting, so we actually have the infinite dimensional setting as well. And so it actually has a lot of, the entropic regularization actually has very nice properties compared to the finite dimensional setting. So it's Fisher differentiable, whereas the Wasserstein distance is not differentiable in infinite dimension. And the Berry center problem is actually much better behaved, because it always has a unique solution. And one other thing is actually the Wasserstein distance, the convergence with the Wasserstein distance actually correspond to this, the weak convergence, and they correspond to the convergence of the covariance operator in the trace class norm, which is the Banach space norm. Whereas for the synchron divergence, we have the convergence in the Hilbert-Schmidt norm. So which is a Hilbert space norm, and can apply lots of large numbers for Hilbert space value random variables of sample complexity. Now for the Banach space norm, we can show almost sure convergence, but it's more difficult to obtain the sample complexity. Okay, I want to show, because this is like we call the also for the Gaussian process setting here, with this is the estimation of the synchron divergence. Here we also have dimension independent. And as I want to say again that it depends a lot on, it uses extensively RKHS methodology. Whereas for the Wasserstein distance, as I mentioned before, we have the Banach space convergence, the trace class norm, which is about an L1 norm. And so it's actually, there are many results for the concentration of like a lot of large numbers for Banach space value random variables. For the case when P is greater than 1, but for the P is equal, it's actually much harder. So in this case, we have the sample complexity here, but it actually depends on the dimension of one of the RKHS being finite. Otherwise, it's vacuous. Okay, so this is just like the kind of the some of the illustrations here. This is kind of the distance between these two Gaussian processes. The Gaussian measures correspond to the estimation of these two distances, and this is for the different processes, and this is for the Wasserstein distance, and the synchron divergence, and the Hilbert-Schmidt distance. Here the interval is for t is from 0.1 to d at power d, and then d is equal to 1, d equal to 5, d equal to 50. So we can see that we have a very consistent in convergence of the Hilbert-Schmidt and the synchron divergence, whereas for the Wasserstein distance, so dimension independent. Okay, so Okay, so I have presented a mathematical framework connecting the two geometrical theory of positive definite operators with the probabilistic and statistical theory of Gaussian measures and Gaussian processes, and we have the generalization of the Fisher-Rao metric and distance and divergences between Gaussian measures from Rn to the Hilbert space setting, but only for equivalent Gaussian measures. And I was talking briefly about the log-net divergences, and for the Fisher-Rao distance, we have the regularization that gives finite distance between any pair of Gaussian measures, and then we have dimension-independent sample complexity. The same for the Wasserstein distance. Even though the exact Wasserstein distance is very nice, the entropic regularization actually is even better properties. So a lot of theoretical properties can actually be obtained, and then we have one of the things I would like to do is actually kind of the generalization of the Hellinger-Kantorowicz distance, which at the moment the formulations are for the finite dimensional setting. I would like to consider for the infinite dimensional setting because it connects information generation and optimal transport. So thank you very much. I'll be happy to answer any questions, comments, suggestions, and criticisms. Thank you very much.
Yeah, thank you for a great talk. So any questions? Yeah.
Thank you for interesting talk. So you defined and obtained many distances on the Gaussian manifold, and can you extend some of distances on this, for example, the mixture of Gaussian?
It's it's a lot more difficult.
Difficult, yeah. Technically.
Even though it seems like it's so not so, it's actually a lot more difficult.
I see. Okay, my second question is the space of SPD manifold in a finite dimensional setup. You can regard this as a homogeneous space, right? G over K. So can you find any sort of infinite dimensional parallel?
I think so. I have not really worked out the symmetric space setting, but I think so.
Yeah,
I think for this setting it should carry over.
Of course, one difficulty is to find that in infinite dimensional setup you cannot find the hard measure.
So that's something that I actually have been asked actually by reviewers actually. So something that to consider for the next actually
I see.
For the symmetric space space actually.
I see. Thank you. Interesting.
So thank you very much.
Oh, I have a very similar question. So you mentioned that like extension with the non-Gaussian cases is difficult, but what is the main obstacle? So I guess that the right-hand derivatives are one possible obstacle. Is the unique only obstacle or more any others?
Well, I think it's difficult because to me it's difficult because it's difficult to get a closed form expression. That's what I mean. That's what I mean by the difficulty. Okay. Maybe we can maybe other properties we can do, but I think for the closed form formula, I think it's very difficult to get. I think. Well, so even for the Gaussian setting with the full mean and the covariance, we actually do not have a closed form formula for the Fisher-Rao distance. Even in finite dimensional setting, actually, we don't have a closed form formula for the geodesic. The geodesic equation is actually so it has not been solved actually. You have only seen either the zero mean. That's why you only say zero. Just a bit. Yeah.
Yeah, I got it. Thank you. So
very simple question. I felt like I walked into Costco, which has too many options of divergences. And yes. So I was wondering, like you talked a lot about Gaussian processes, but natural gradient descent is the method now for Gaussian processes. Yeah. So do you know if there's any ideas on how to use all of this stuff, or?
We need to talk.
Okay.
We need to talk.
Oh, well, our offices are very far, just like one room away, so it's hard to do that. Let's do that next time.
Let's do that.
So, any other questions? Okay, so that's all. So please thank you, speaker, again.
Thank you very much.
Thank you very much for the invitation. So I promise one thing, I'm not going to have 62 slides, but only 12 slides. So it will be a bit quicker. So I'm going to talk about the Fisher-Rao gradient of the evidence lower bound. And I'm starting with some review of generative models and also with the intention to fix notation here. So this is a general picture here. So you have a system, let's say a neural network, which consists of visible nodes and hidden nodes. And so that defines a set of probability distributions, which is sitting in the set of full set of probability distributions denoted here by P or P index V, comma H. So this is a set of probability distributions on all states of the system consisting of visible and hidden states. So, and then we have, of course, the probability distributions that on only the visible states. So it's denoted by PV, and we have the natural marginalization map, which takes the joint probability distribution on the full system and marginalizes out the hidden states. So this way we have a nice mapping here. So usually, if we want to do learning, it would be natural to consider a model sitting in PV, so in the set of probability distributions of visible states. So that would correspond to MV, but that's not the general the general approach that people usually use. So they consider a statistical model M sitting in the set P of probability distributions, so on the full system, and then consider the marginal of this model, which is simply the image of calligraphic M under the map pi V. And this is denoted by M index V. So this is the marginal statistical model in PV. So this is a notation. The target of this kind of network is actually to generate a target distribution P star. So P star is a probability distribution on the visible states, and you measure simply the Kullback-Leibler divergence between P star and a probability distribution P in the model MV, in the marginal model. So this is the explicit expression here. And this is the primary objective function usually considered to train a generative model. But there's some ambiguity here. So we could consider P, as I said, as an element of MV, but as I described before, the set MV is coming from a model M in the full space. So we could rewrite this P of XV into this sum here, which basically interprets this PV, this P as the marginal of a global probability distribution P. This seems like an unimportant fact here, but it plays an important role because these are mathematically two completely different functions. So this function is defined on the marginal model, and this function is defined on the global model M. And if you want to do the natural gradient, you want to apply the natural gradient method, you would use the natural geometry, in particular the Fisher-Rao metric on MV in this case. And in this case, you would choose the Fisher-Rao metric on M, which gives you different results. So when training a generative model, it turns out that it's highly beneficial to also consider a so-called recognition model. For example, the famous Helmholtz machine has been proposed by Diane, Hinton, and Neal in 1995, where they propose a generative model in terms of generative weights. So this is the top-down direction, which corresponds to the top-down direction that I had on my previous slide. And then there is a bottom-up direction, which is referred to as recognition model and expressed here in terms of recognition weights. And they propose a way to learn the target distribution by actually adjusting the generative and the recognition weights in a particular way. They use the so-called wake-sleep algorithm and apply the Kullback-Leibler divergence in a way that is often stated to be not very natural because they have two kinds of Kullback-Leibler divergences. This has been overcome by by this work here, by the work on the variational autoencoder, where they have only one objective function, and that's the evidence lower bound. So I'm going to talk about this, this evidence lower bound. So let's go back to the primary objective. So it's this Kullback-Leibler divergence between P star and P, in where P is taken from the marginal model MV. That's of course equivalent. So minimizing this is equivalent to maximizing the so-called evidence or mean evidence, again, P taken from MV. And now we replace again this P of XV by this sum. And it seems to be a trivial step, but actually this is not necessarily equivalent. It is intuitively equivalent. But if we want to optimize in terms of the Fisher-Rao metric on M, now P is taken from M, then it's not necessarily equivalent. But anyhow, so it's not equivalent in the sense of having the same natural gradient, but it is equivalent in the sense that when you maximize this quantity, you will also maximize this quantity. Now the evidence, this mean evidence, written here again, can be lower bounded by this quantity, incorporating now a recognition network, which is referred to as the elbow, the evidence lower bound. So we have this lower bound, and the difference between the left-hand side, so the function that we want to optimize, and the lower bound is referred to as the gap between the two functions. And obviously, if the gap is small, we expect the optimization to be good in terms of really giving us a good generative model. But if the gap is large, then the method of optimizing the elbow is usually considered not to be very good. And I'm going to provide an information geometric argument why this can be still very good. So let's interpret the quantities that I have just introduced in terms of information geometry. So we have the set of marginal distributions, which PV, so this is this horizontal line. And then we have the vertical direction, which basically describes the additional dimensions that we have to incorporate in order to describe global probability distributions. So that's the full set. And the horizontal line is the set of marginal probability distributions. So the model M, calligraphic M, is sitting in the full set. And now we have the marginalization map denoted by PV. And we define in the full set, the set of all joint distributions Q, for which the marginal equals P star. P star is the probability distribution that we want to approximate, or from which we want to actually generate. So we have this natural projection of the full set Q, calligraphic Q, onto this single point P star. And in terms of information geometry, this is referred to as an M-convex set. Now, in addition to pi v, which is the marginalization, we have the differential of pi v, which takes the tangent vector from the full set into a tangent vector of the marginal set. And we need also to define the kernel of this pi v, so denoted by Vp, and the orthogonal complement of the kernel. So the kernel goes in the vertical direction and the orthogonal complement goes into the horizontal direction. And the orthogonality here is meant to be orthogonality with respect to the Fisher-Rao metric. So this is just to explain this picture here. And now let's have a look at the Kullback-Leibler divergence between a point Q in calligraphic Q and the point P in the model. So this can be decomposed via the Pythagorean relation in terms of Kullback-Leibler divergence from Q to pi q of p plus the Kullback-Leibler divergence from pi q of p to p. And pi q of p is simply the E projection of p onto this M-convex set, which basically means that it minimizes the Kullback-Leibler divergence with respect to the first argument. So this is the decomposition. And if we look at this decomposition more carefully, the first term, which is basically this term, is exactly the gap that we want to study, the gap that I have introduced before. And the second term, this term here, is exactly the function that we want to optimize. So now let's take the gradient of these terms here. So we have these terms, and we now consider the Fisher-Rao gradients of these terms. So the Fisher-Rao gradient of the gap taken in the full set P is simply the difference vector q pi q of p minus q. It's this one here. So it's pointing into the vertical direction. So the gradient, the Fisher-Rao gradient, points into the vertical direction. The Fisher-Rao gradient of the second term of the Kullback-Leibler divergence, so the function that we want to optimize, points in this direction. It's p minus pi q of p. So it's in the horizontal direction. And of course, the Fisher-Rao gradient of the sum of the two is simply this vector here. Now, if we want to do the natural gradient method, apply the natural gradient method on M, we have to project that vector or all the vectors onto the tangent space of TPM. But just in order to illustrate the mechanisms that I'm trying to highlight here, let's ignore this projection and let's consider the calligraphic M to be simply the full set. So we only deal with these Fisher-Rao gradients. Now we consider the differential of these Fisher-Rao gradients. And because the Fisher-Rao gradient of the gap is pointing in vertical direction, which is the kernel of the differential maps it to 0. And the Fisher-Rao gradient of the actual function that we want to optimize is mapped to the difference vector here, which corresponds to this difference here in the horizontal line. And the Fisher-Rao metric, Fisher-Rao gradient, the differential of the Fisher-Rao gradient of the full Kullback-Leibler divergence is simply the projection of this difference vector, which is again this difference vector. So what I want to highlight here is that the gap, even though it might be big, its differential, the differential of its Fisher-Rao gradient can be 0. So it can be mapped to 0. So having a large gap does not mean having a bad approximation of the original function P star. But again, this works for the moment, I'm only considering this in the full model. So this is what I just said. So if we do the Fisher-Rao gradient in the full model of the elbow and then take the differential, it turns out that it's exactly the Fisher-Rao gradient that we want to have on the visible space. That implies that if we first solve this differential equation in the full system with the elbow, which means if we do natural gradient with the elbow and then project that solution, so that's denoted by gamma here, and project it to sigma, the projected curve will also solve the differential equation of the original objective function. So in this sense, the elbow is, even though it's a bound, it's a perfect bound. So the gap can be large, but it gives us the same solutions. But again, this only holds for calligraphic P for the full set. So now let's consider the restricted set. It's based on the following question. So again, we have the full set of probability distributions and the marginal set of probability distributions. and we have an objective function which is actually defined only on the visible distributions. So it's denoted by L here. Now what we can do the Fisher-Rao gradient of L. This is what we call the natural gradient, but we can also do take the composition, so the marginalization, and then L, applying L, and do the Fisher-Rao gradient on P. And now the question would be, is the differential of the Fisher-Rao gradient here, so the Fisher-Rao gradient here, and you take the differential, this gives you a vector in the tangent space of PV. Is that the same as the Fisher-Rao gradient of the original function L? And it turns out that this is the same, if you restrict the tension, if you consider the full set P and PV. So this is a very nice equality here. So it does not matter whether you optimize in the full space or in the marginal space. But now comes the restriction. So you take a model as a submodel of P, and then its marginalized model, it's sitting in is a submodel of PV, and we can ask the same question. And that unfortunately does not hold anymore in general. And in order to specify those models for which this does hold, we have to introduce the notion of a cylindrical model. So as I said, PV is the marginalization, and the differential of pi v is denoted by d pi v. We have again the kernel of dp pi v, so of the differential, and the orthogonal complement of the differential. So this is the vertical direction, this is the horizontal direction. And the model M sitting in the full space P is called to be cylindrical if its tangent space in any point, non-singular point P in M, the tangent space is simply the sum of the tangent space intersected with the horizontal direction and the tangent space intersected with the vertical direction. So this is highlighted here. So this is the full tangent space. If you take that tangent space and intersect it with the vertical direction, you get this line here. If you intersect it with the horizontal direction, you get this line, and the sum of these two lines gives you the tangent space. So this is a cylindrical model. Now the main statement is that for this original question, so if we restrict in this diagram, commutative diagram, to the model M and MV, this again holds. So this equality holds, is stated here again, if the model M is cylindrical, which is quite restrictive. So in general, it will not hold. And it's actually, there's a stronger statement. So such an equality holds if and only if M is cylindrical. But one has to specify that statement more clearly, which takes more space. This is why I have omitted it. And the proof goes along the lines of chance of uniqueness theorem of the Fisher-Rao metric. So based on this theorem, we can actually prove that for cylindrical models, the differential of the natural gradient of the elbow is exactly the natural gradient of the original objective function. And again, if we solve the gradient, this differential equation with the elbow in the larger system M, so calligraphic M, and then project that solution down, it will give us exactly the solution of the original function. So this is very nice, but so again, this states that for cylindrical models, even if the gap is large, it could be it is actually the fact that the optimization of the elbow, the maximization of the elbow in terms of the natural gradient method is exactly equivalent to the natural gradient method on the original objective function on the visible states. Here's an illustration. So as an illustration, we have considered here two graphical models. So one is simply the independence model. So these are T1 and T2 highlight the visible nodes, and S is the hidden node, and we marginalize out. So this is, and the fact that there are no edges between these three nodes means that the joint distribution is a product distribution. And if we marginalize out the hidden variable, we still have a product distribution, which means that the projected model MV corresponds to this surface here, to this two-dimensional surface, if we assume the nodes to be binary. And now you can consider the difference between the natural gradient on the visible nodes of the original objective function, which is the red line here, and then the dashed blue line is the push forward or the differential of the natural gradient on of the elbow. And they coincide because this is a cylindrical model. If we add these edges here, these arrows, we get a graphical model which is not cylindrical anymore, and we see a difference in the visible nodes. So again, the red line is the natural gradient of the original objective function, and the dashed blue line is the differential or the image of the solution of the natural gradient equation in the full system. And you see the deviation here. So, and this deviation is expressed also in terms of the coordinates and also in terms of the Kullback-Leibler divergence. So that's my last slide. I want to summarize. So we have seen that we can actually even if we have a large gap, the elbow gives us exactly the same optimization process as the original objective function if the model is cylindrical. So now you could argue in the most simple diagram here, the most simple model, you won't have a cylindrical, the property of being cylindrical. That is true, but the idea would be to actually, for a general model, to measure how much it deviates from being cylindrical, and we have corresponding equations for that. And that could actually give us a measure on how much these solutions will deviate from each other. So the results I have presented are initial results that might allow us to provide more refined results that with which we can measure the difference between the two trajectories. But the general message is that the large gap does not mean a bad optimization. And that's, I would say, the take-home message of my presentation. Thank you very much.
Yeah, thank you. Thank you for your great talk. So is there any question or comments from audience?
Yeah, thanks a lot. This is amazing. Very, very happy to hear that the gap doesn't ruin everything. I was wondering, this thing about the cylindrical thing that you presented, is there a way to somehow understand how that goes back to the property of the original posterior? Like, if things are hard, then if the posterior is very intractable, then somehow this should reflect in this property. Do you have any thoughts on that?
So basically, it has to have a, so if you consider a set of posterior distributions, which are conditional distributions of Q of XH given XV, And let's call that, so that's a fixed set, and you multiply it with P star, so that you have a foliation, so to say, that corresponds to this fiber here. So this would be the situation where you get this equality of, you have this property of being cylindrical. So you need to have an somehow a vertical component that stays locally invariant. How that is related to the, let's say, to the posterior in terms of graphical models, I can't say at the moment.
Okay, fair enough. I'll have a look at the references. Thank you.
Yeah, thank you.
So, any others? Okay, so it's almost time to so let's close the question. Yeah, please thank speaker again. Thank you.
Thank you very much.
Okay, I retired RIKEN Research Institute about 8 years ago, and I enjoy doing study as my hobby, not a profession, but as my hobby. So my hobby is playing a Go game, computer software, and enjoying some scientific research. But now maybe it's my time limit. So I'm afraid that maybe this is my last talk in those international conferences. And I'm interested in something, the Wasserstein geometry, because and I am interested in the manifold of probability distribution. Okay, and so it's very important for statistical inference or machine learning and so on. But recently, the Wasserstein geometry can becoming the more and more in this community. So what is the difference between Wasserstein geometry structure and information geometric structure we have worked so far? So a pointer here, okay. So think about manifold of probability distribution P of X. Okay, X is just something n-dimensional Euclidean manifold or something. What is the natural geometry to be introduced? There are two geometries. So one is Fisher-Rao geometry based on the likelihood or something of those things. And maybe more mathematically, it's based on invariant principle given by Chenzo. But the other Wasserstein geometry is much older, maybe 300 years ago, and it's okay. So Wasserstein geometry can be defined, for example, by using a divergence function between two probability distribution. Okay, and say KL divergence, something like that. It measures the difference of Px and Qx at point X and doing average. So if Q is 0, there's some problem. In such a situation, we can use Hellinger divergence or Hellinger distance. But Wasserstein divergence, we measure the difference between P and Q by moving point inside this Px to point to Qx in the optimal way. What is optimal? We need the cost function from a point X move to point Y. And usually cost function is a function of Euclidean distance between 2 points. Okay? So it looks like Wasser geometry measures the divergence between P and Q by using horizontal way. How? We need to move things in horizontal way. But in the case of scale divergence or something invariant divergence, we measure the difference from P and Q at point X. That is the vertical difference, and do some average. It looks very similar, okay? But the structure is very different. As I mentioned, yes, the vertical or horizontal. And so, usually, the treatment in function space is really different because topology comes in and a lot of conditions needed for discussing function space. So I am not a pure mathematician. I don't like such complicated thing. I like to think about the parameterized model, P of X and theta, where X is a random variable, theta is a finite dimensional parameter. Okay? Say in the Gaussian distribution case, say mu and sigma, it's two-dimensional. In neural network, it's a lot of connection synaptic weights included. It's huge model. But anyway, so the problem is we think about the Fisher-Rao estimation and Wasserstein estimation, and that we observe from x1 to xn, n samples from the same distribution. And we want to estimate the parameter theta from which those observations come in. The first thing we do is we calculate, and this is the empirical distribution, just a histogram. Okay? And it maybe sit in this space of probability distribution, but it's non-smooth and something very bad one. But forget about that one, and we want to model manifold parameterized by theta. And the estimator theta, we project this one to model parameter. And such that distance or divergence from here empirical distribution to model distribution is minimized. In that case, divergence measure plays a role. Okay? By using Fisher-Rao divergence or Cade divergence, or something the Wasserstein divergence. So far, in the community of mathematical statistics, they used those Fisher matrix and the Fisher efficiency, and all those things are very popular and successful. Okay, then why we can't construct double Wasserstein statistics that is using the Wasserstein divergence? Okay, and so given this one, we have something, the shortest one, if we can easily prove that empirical distribution converges to the true distribution in distribution. Okay, so in both estimators are consistent. The second thing we talk about is efficiency. Is it efficient or not? And okay, so and it is proved that yes, something efficiency discussion, we can have the maximum likelihood estimator. That is the Fisher-Rao estimator is the most efficient in the first order and even in the second order. Okay? So in statistics, it established that the maximum likelihood estimator is one of the best one. How about the Wasserstein estimator? Okay? Maybe it's not efficient. That implies estimation error is bigger than Fisher estimation, but there might have some merit of using Wasserstein geometry and at the cost of loss of efficiency. Okay? For example, I was impressed by more than 10 years ago, Marco Turi. He sent me a paper showing that there are lots of patterns, okay? Pattern distribution. And he wanted to calculate the center of gravity of those distributed patterns. He used Kerr divergence, Hellinger divergence, and many others, showing that Wasserstein estimator is the best. I don't know if best or not, but very excellent, keeping the shape, some common shape of those probability distribution. Why? Okay. It maybe Wasserstein geometry is very good, not estimating a parameter, but searching for some common thing inside the shape of probability distribution. Of course, recently, the diffusion model is so fashionable in AI community, and we can easily prove that the diffusion model is based on the, in some sense, Wasserstein structure. Okay, so there's a very good sense in the shape analysis and those Wasserstein geometry. Maybe I don't need to talk about something, the Wasserstein divergence. We use L2 Wasserstein geometry. Okay, so cost function is the square of the Euclidean distance between two, and we want to minimize the transportation cost from P to Q. That is Wasserstein, and there's a nice theory. In the case of Wasserstein geometry, there is a dynamic formulation. So that in order to move from P to Q, we have something depending on time parameter and transport X to something Y, okay, along the path. And we can formalize the Wasserstein distance can be defined in terms of those velocity vector, which has some potential function and so on. And for the case of the diffusion model, it fits very well. Okay, so we can think about Riemannian metric in the function space. Maybe in general, Riemannian metric is to think about small deviation of P of X, and its quadratic form may say something small distance, Riemannian distance between the two. In this type of formulation, in the case of Fisher case, we use this one as 1 by Px, where here is delta function. And that implies the square distance is deviation of logarithm of P. Okay? And we just square. And in the case of Wasserstein geometry, we can have dynamic formulation. And finally, we obtain Wasserstein Riemannian operator is minus inverse of Laplacian P, where Laplacian is gradient and multiply P and take divergence. Okay, so it is P Laplacian. They found this is automatic. Okay, and we wanted to something integrate the F geometry and the W geometry. And however, it's not so easy, but yes, the Couture theory impressed me to motivate to do that by introducing an entropy linearization. And we have done that a little bit. And recently, Professor Lee proposed a nice theory, unifying F geometry and the W geometry. So he used the score function to integrate both frameworks. Okay, so we think about parametric model, it's finite dimension, and small deviation of probability is just a gradient with respect to theta of this probability distribution. Okay, and we multiply, we operate G Riemannian metric to this one deviation of probability distribution. And so it is a covariant vector, and multiplying by B, it becomes contravariant vector, showing the tangent direction of this one. But forget about the details. But anyway, in the Fisherian geometry, this is just a score function. Okay, so gradient of log probability, and Wasserstein case, it's just operate the inverse of Laplacian to the IP. Okay, how we calculate this one, inverse of Laplacian P, it looks very difficult, but they showed that, and it is known that this score function is a solution of such types of Parsonian equation. And the nice thing about the score function is its expectation with respect to true distribution is 0 in either case. Okay? So that implies we can use other to obtain estimator theta that instead of expectation, we use empirical expectation. So just a summation, and this is estimating equation. If we have such functions, such set of functions, we have estimator, and it is consistent, we can prove that. So we are talking about the, and so this gives a practical means of projecting empirical distribution to manifold, and in terms of Fisherian way or Wasserstein way. And in the case of Fisherian case, we have Kramerov in Nicole showing that the Fisher estimator, that is maximum likelihood estimator, is one of the best estimator in the sense minimizing error. What about Wasserstein estimator? We have another type of the inequality showing something, the property of Wasserstein estimator, but here not covariant. This is error covariance. Here it's different covariance defined in terms of Wasserstein geometry. But forget about that because it's not so. I don't want to go, yes, definition in this one, but maybe so intuitively understand. So we can prove that if our sample X is noisy version, x plus n. That implies probability of x prime is deviated from the waveform of probability of originality by convolution of noise distribution. Okay? In that case, we can show the Wasserstein estimator is one of the best that does not have great difference from the original. So no Wasserstein estimator does not minimize estimation error, but minimize in some sense robustness against perturbation of the probability shape. So I'm interested in showing how the Wasserstein statistics are affected by the shape of the probability distribution. Okay? And so we now consider a very simple model that is affine deformation model. We fix probability distribution of z is x, that this is the probability, it's centered at the origin, and its covariance matrix is identity matrix. So we say this is standard shape. And think about, so given any probability distribution, we can standardize it by shifting the center and also by doing some affine transformation, including rotation. Okay? So then a probability distribution can be decomposed in the shape part and this deformation part. Deformation, the affine deformation. And the good point, so we see this is the manifold space of all probability distribution. And if we have subspace consistent of all standardized probability distribution, that its shape only is important. Position, size, those does not matter. Okay? And we decompose it into this standard distribution and affine deformation. Okay? Position, rotation, scale, and so on. So then, for given one standard model, we have manifold probability distribution MF given F. F can be, for example, Gaussian or something like that. And good point of Wasserstein geometry is this shape manifold and the deformation manifold is orthogonal. Okay? Well, this is very good, but in Fisher-Rao geometry, it's not orthogonal. So it's very good to decompose the shape and also deformation parameter or position parameter. Now we need to calculate the W score function, solving this type of equation. Okay. But in the case of affine deformation, we can solve this deformation equation giving the score function of x, where parameter is lambda and mu, is in a quadratic form. Okay, it's a quadratic form. This is something constant, not dependent on x. And score function for location parameter mu is only linear function. So this can be easily solved to give Wasserstein estimator in this the affine deformation model. Okay, so the Wasserstein estimator is the moment estimator. That is, they need to match moments. Okay, very simple. And it is no moment estimator is not good, not efficient. Okay? However, robust against the change of waveform. Okay, interestingly, this estimator does not depend on shape F. In whichever shape we have this Wasserstein estimator. Okay, so interestingly, for each MF, the Riemann metric is Euclidean, very simple. Okay. So now maybe my time is coming, and so then one thing is so the W estimator does not depend on F. On the contrary, the maximal likelihood estimator highly depends on the shape of F. If F fluctuates a little bit, okay, maximal likelihood estimator changes greatly. So, okay. And so we need to do a lot of work. First, we talked about the Wasserstein Riemann metric inside MF. It's very simple. But in this shape direction, what is what the Wasserstein metric shows? It's another problem. And also, recently we are talking about flow of probability distribution. That is the diffusion model does. Okay? In terms like the depending on Wasserstein. So we want to know, given dynamical flow of probability distribution, then is there any good Wasserstein geometry, that is Wasserstein cost function, that describes this flow in terms of the minimizing new Wasserstein distance? Those things still remain. And as my hobby, I want to do work, but today I found I am too old. Okay, so thank you very much for hearing me.
Thank you for your great talk. So any questions or comments from audience?
Thank you very much. I have a question. So in your presentation, you highlighted the Euclidean distance or square Euclidean distance as a cost. I have seen some recent works that look more closely into using maybe Bregman divergences or other types of costs. Yeah. Do you think some of the tools, of course, many of the tools that typically associated with dynamic formulation work well with squared Euclidean distance, but I'm wondering if you see other interesting directions in using other base geometries or costs.
Okay, so very good point. And so K-ed divergence, curvature divergence is non-symmetric. Okay? And it played something good role to define dual structure in the manifold probability distribution. However, the ordinary W estimator depends on the cost function, which is ordinary symmetric. So Riemannian structure only comes in, but no dual structure. However, something I think it's wrong. They introduced as a cost function some Bregman divergence between Q and Y. Okay? Then we have a non-symmetric Wasserstein divergence in terms of minimizing those transporting costs. And we have the something world of dual affine connection in this case. It's dually coupled, not necessarily dually flat. But this is something in new direction to integrate F geometry and W geometry. Thank you for your comment.
Thank you. So any other? Yes.
So thank you for your talk. And I think a main problem with this Wasserstein geometry is that it could be difficult to compute the Wasserstein score. So is there like a method to at least approximately calculate the score efficiently? Like calculate the score function efficiently.
Okay, we are lucky in the affine differential model. It's so simple, and we can solve that the differential equation to obtain. But in other model, for example, in the shape manifold, and how to calculate the score W square function is maybe problem. I'm thinking about, for example, the very simple case that shape function is something like SPX, two-dimensional case, say C exponential. Very simple model depending on P. If P is 2, it's Gaussian. Okay? And so in the Gaussian case, like it's this way. And if P goes to infinity, shape goes to square. It is distributed over the square type. And if P is smaller than 1, this is something like this way. Distribution over in this shape. This is one-dimensional, very simple model for this describing shape change. How is the score function and how is the W metric in this such simple case? Okay? And I want to calculate, but maybe it's too difficult to me. So it's up to you to calculate more and more the geometrical shape in terms of Wasserstein geometry.
Thank you.
And I have a very simple tiny question. So at the beginning of your talk, so you mentioned that the Fisher-Rao is kind of the vertical distance, and Wasserstein is like a horizontal distance. And my simple thought is that how about the diagonal type? So is it possible to develop kind of the
introducing something new divergence?
Yes.
Both integrating. Maybe, of course, simplest idea is just addition.
Yes.
But it's not so indirect. More structure we need. Thank you for very nice comment.
Thank you. It's my interest. Okay. So it's almost time. So let's close this session. So please, some speakers again.
Thank you, everyone. Professor Amari has been a source of inspiration for all of us for many decades. So I would like to dedicate this little talk to him. And I'm sad to hear that he's retiring from international talks, although I don't believe him completely, but this talk is very simple, much more simple than the previous talks, but it has a little bit of geometry, and this is why I think Professor Amari may appreciate it. And at the last workshop we had at RIKEN, he gave the talk on the whiteboard. So I'm following on his steps, but now he went back to PowerPoint. So, okay, so very classical situation. Imagine you have a huge neural network with, let's say, 1 trillion neurons. So bigger than GPT-4. Let's say all the neurons are ReLUs. And let's suppose your error function has 2 things, as usual. It has the data-dependent portion. So for instance, the negative log likelihood, typically, the least square or relative entropy, but it could be anything you want, plus a regularizer. And let's say that the regularizer is L2 for now.
So it's the sum of the weight squares. Okay? Something you do every day. And so now you train this by gradient descent very carefully on some data. And after training, you end up with this big black box that has 1 trillion neurons and maybe 100 trillion parameters and so forth. Everybody's crying, it's a black box, there is no structure, etc. But Professor Amari is very optimistic, and so he's gonna put a microscope on one of the neurons. So you have a neuron here, I'm going to magnify. It's a ReLU neuron, so it is like this, transfer function. It has a bunch of weights coming in and a bunch of weights coming out. And you look at this neuron under the microscope, and suddenly you're gonna see something amazing. You're gonna see that the sum of the weights coming in, weight squares, is approximately equal to the sum of the weights going out. Anybody has seen this before in this room? Nobody. Okay, sorry? I'm getting there. So you get this amazing relation, which I call synaptic balance. Converged. Initialization, there's no reason for that, right? That's the convergent. After convergent, you find this for this neuron, and you go and look at the other neurons, and all the neurons satisfy this. The norm of the incoming weights, L2 norm of the incoming weights, is roughly equal to the L2 norm of the outgoing weights for all the neurons. That? Connections, layers, no. Anything. Doesn't even have to be feed-forward, can be recurrent. Okay, so what we're gonna do first is to understand why this happens. Does it depend on L2 and does it depend on ReLU? Okay? All right, so let's think about a ReLU neuron, and I'm gonna define a very simple operation which I call scaling, where what I do is multiply the incoming weights by lambda, where lambda is a positive factor, and I divide the outgoing weights by 1 over lambda. Okay? What happens in a ReLU if you do this? Well, let's suppose the activation was negative. I multiply by lambda, it goes more negative, nothing happens. The output is still 0. You send it on these wires, nothing changed. Okay? Activation is positive. Here on the positive part of the ReLU, it's the identity. So it gets multiplied by lambda, divided by lambda, nothing happens. In other words, the total input-output function of the network doesn't change at all if I multiply by lambda and divide by lambda if I do this scale. Okay? That already tells you that there is a manifolds of weights associated with all these scalings of all the neurons that keep the performance of the network with respect to the data completely invariant. Okay? That's one of the reasons why they don't overfit, is because the data doesn't need to specify the exact weights. It only needs to specify some equivalence class. But that's a different story. All right. So now we're going to define another operation. By the way, scaling is a commutative operation. So if you scale one neuron by 5, another neuron by 7, the order doesn't matter, even if the neurons are connected. Because if you have a connection like this, from neuron I to neuron J, you multiply this one by, actually, let's write it from J to I. You multiply this by lambda J, this one by lambda I. This connection here, Wij, is going to get multiplied by lambda I over lambda J, and again, the order doesn't matter. Okay, very simple. Now let's define another operation, which is called balancing. So I take any ReLU, I multiply by lambda, I divide by lambda, nothing changes here. But of course, it makes a difference here. So we could ask, what is the best lambda that minimizes the regularizer? Very simple question, right? All right, so what's the contribution of this neuron to the regularizer? Very simple. It's the sum of the lambda W square incoming plus the sum of 1 over lambda W square outgoing. You tell me if I make a mistake, okay? All right, good. So now we want to minimize this over lambda. Oh, now we have to take derivatives. Well, that's too difficult. Professor Amari and I, we forgot how to take derivatives. We forgot completely. Especially derivative of this is a nightmare. But we know some geometry. So we're gonna say, imagine these two, so this is of the form lambda square A plus 1 over lambda square B, of course, where A is just the sum of the square norm of the incoming weights and so forth. All right, imagine these two quantities are the sides of a rectangle. The product, the lambda goes away, so the product is constant. And so you're looking at rectangles that have a constant area, and the smallest perimeter is for the square. So I know the lambda optimal is gonna be when these two guys are equal. So when I set them to 0, I get B over A to the 1/4. Tell me if I make a mistake. Okay? Everybody agrees? Great. So that's the optimal lambda. When you put so you're gonna multiply the weights by the optimal lambda, and you're gonna get a neuron that is in an optimal state. And at the optimal state, if you try to optimize against the lambda has to be equal to 1. So at the optimal state, you get that B equal A at optimum. In other words, the neuron is balanced. The sum of the square of the incoming weight is equal to the sum of the square of the outgoing weights at the optimum when the neuron is balanced. Okay? Now, balancing is not a commutative operation. If two neurons are disconnected, it doesn't matter. Yes, you can commute. But if they are connected, you cannot commute things because if I balance J, it's going to change this weight, and so it's going to change the lambda star of this neuron and vice versa, right? So balancing, this is commutative. Commute. Balancing commute as a scaling operation, but otherwise it doesn't commute as a balancing operation. Does not commute. Okay, everybody is with me so far? More or less? Okay. Now, let's suppose I don't like L2 and I want to do L1 or L7 or whatever L you like. Does it change anything? Not really, because you're going to get, all this is the same. Here you're going to get power P. So you're going to get a lambda P, 1 over lambda P. So you get a lambda 2P, but then all the rest stays the same. Right? So if you do L1, you get a balance equation. The sum of the L1 norms of the incoming weights has to be equal to the sum of the L1 norm of the outgoing weights. So it's very general. It's true for any LP, P greater than 0. You're going to see this balance. Okay? So if you have a friend or a student or whatever that trains a network and comes back to you and say, oh, I trained a network, you check if everything is balanced, because if it's not, it means the training was not good. Okay, so you have a trick now to check whether people are training networks properly. All right, what about ReLU? Is this true only for ReLU, or is it more general? What did I use? I used the fact that, so F is homogeneous if and only if for every lambda positive, f of lambda x equal lambda f of x. Okay, that's what I used when I did this little scaling thing. Okay, so what is the class of neuronal activation function that satisfies this equation? It's very easy to show that it's the class, so this is equivalent to being a what I call a bilu neuron. Bilinear, but basically it's two lines, right? So anything ReLU is good, leaky ReLU is good. So leaky ReLU looks like this. The identity is good, so linear neurons would have all these properties and so on. Wedge, some people use this activation function. Anything that is made by two lines intersecting at the origin is homogeneous, and this theory, this little balancing business would apply. Okay? You want to go beyond that? Sure, you can. Suppose I multiply by lambda, and the output gets multiplied by lambda squared. I divide the outgoing weights by 1 over lambda squared, right? So there is more generality that can be derived at the level of the transfer function, but I won't, let's not get into there. This is already good enough. If we have all the ReLU, all the linear function, all the leaky ReLU, that's pretty good for most applications. Yes?
What if there's no regularizer? Is it looking different? Or?
If there is no regularizer, there is no reason for having a balanced network at the end of training. By the way, why is the network balanced at the end? Suppose you train it and you finish training. And I look at this neuron and it's not balanced. By balancing, I can go further down by reducing this part of the error, right? So that's why if it's trained properly with small error rates at the end, et cetera, you need to see balance everywhere. In fact, exact. In principle, you should see equality everywhere.
So if I do early stopping something or something.
If you do early stopping, there is no reason for having balance at the early stopping time. Okay? Other questions? To be balanced? Well, if gradient gets you there, it must be good. I mean, gradient is everything. Well, the regularization then is L2 good? You can put L2 plus L1. This all works. It works on, almost on any regularizer. It's very general, actually. Okay. Sorry? Yes. But we can talk, let's not go. Okay. Other questions before I show you the main result? This is not the main result. I'm not sure exactly what you mean by frequency content.
I mean, you can say you want to have low frequency function. I mean, with a low frequency function.
That's why you have a regularizer, right?
Yeah, that's what I'm saying. If you physically put a regularizer like that.
Oh, you want a logo? Well, but what is such a regularizer? I would have to see the mathematical form. I mean, I know roughly what's the general form for the. Let's check. Let's check after the break. Okay. Any other questions? Okay. But this suggests another idea now, which is, I mean, at any time you can balance a neuron, right? At the beginning of training, when you have random weights, in the middle of training, at early stopping, anytime you want, you give me a network, I can go take a neuron and balance, do this little thing and put it in a balanced state. It doesn't change input-output function, everything is fine, right? And I can balance this other one, and so forth. So I can go through the network and balance neurons in any order you want, stochastically, layer by layer, whatever. Let's suppose you start balancing neurons throughout this network, okay? When you balance a neuron, you may break the balance of another neuron. So the question is, what happens if you do this stochastic balancing of the neurons in the network at a fixed state of the network? Doesn't matter which one, but you start with a fixed set of weights, and then you start balancing neurons, let's say at random, completely stochastic. Okay? Does it converge? Where does it converge, and so on, right? So the answer is that it converges. It's easy to see that the regularizer converges, because every time you balance a neuron, the regularizer either goes down, either stays the same if the neuron was already in balance state, right? The balancing always reduces R. R is always greater than 0, so it goes down. At some point, it has to stabilize. So the regularizer always converges, but that doesn't mean that the weights are converging or that the state of the network is converging. So the answer is yes, the network converges, the weights converge. That's interesting. But the most amazing thing is that it always converges to the same state. It doesn't matter in which order you apply this balancing, this stochastic algorithm throughout the network, it always converges to the same set of weights. Do you believe it? Okay, why?
It will have to depend on like.
I'm sorry?
Learning rate stuff by this, I don't know.
No, there is no learning rate. When you do balancing, there is no learning rate.
But then,
if I have an initial network with an initial set of weights and the neurons are not balanced, I start balancing the neurons, okay? This part doesn't change. This guy starts going down. You arrive to a fixed point, which depends, of course, on the initial weights. You're not going to get the same fixed points if you start with random weights or in the middle of train. That's true. But for an initial set of weights, you're going to always converge to the same configuration, no matter in which order you're balancing the neurons. It's invariant under the balancing, if you want, under the order of the balance. Yes.
You may have about this very shortly, but if I change the riser from say L2 norm square to LP P square, also they are kind of like a balance, but now in terms of LP norm
Yes.
to the power of P. I was wondering, I mean, I get the same kind of like invariance phenomenon with the different kind of LP norm. Is there any difference in terms of translation by shooting different in terms of balance from the fact of that?
In terms of balancing, they get balanced with respect to whatever LP you are using.
Right, but is there a difference of the conversion network in terms of translation?
That's a different question. I'm not touching generalization.
Just to add to this question, assume you would like to balance quickly, right? Is it better to start with LP and then go down to L2 or L1, or, you know, is there any experience of that?
There is two different questions there. There's two different questions. One is playing the games. For instance, you could train gradient descent on L2, get down, and then do a balancing on L1. That could be interesting, maybe to prune the network, stuff like that.
I think my question was if you just consider the balancing, you could, you know, consider the balancing, you know, with a different, you know, like with an annealing of the regularization part, in a sense. So you could use different regularizations, do the balancing, and because you do it randomly, you know,
You're saying, let's take this neuron, let's do L2 balance on this one, and do L1 on this one, L7 on this other one. That would lead to a mess. Yeah, that would be very messy. I mean, I haven't thought about it, but.
I'm just trying to explore because we may have thought about it.
Okay, other questions? So why does it converge to a single state? That's the question now. So let's try to understand that. Do we have time? Yes. So let's look at one connection here, Wij from neuron J to neuron I. And you are multiplying this one by lambda J, this one by lambda I. Now remember that the balancing operations are not commutative, but they are commutative as scaling operations. Okay, so once you start balancing at random throughout this network, I can always permute those scaling operations, not as balancing operation, but I can permute them so that I put all the scaling of the first neuron together, all the scaling of the second neuron together, et cetera, et cetera. So after time t, what happens is that you have scaled this network by some quantity like this, where this is the product of all the little lambdas that were applied during the stochastic algorithm. So if you balance neuron J 10 times, you visited it 10 times during your stochastic balancing, this one is going to be the product of the 10 numbers that were used to balance neuron J. Maybe you have to think a little bit about that, but that's what it is. Okay? This is because of commutativity, you can reorder the balancing operations. So the way Wj after time t has become Wij times lambda it over lambda jt. And so basically, you're interested in what is the behavior of this quantity, right? For the weights to converge, this quantity, for instance, has to converge. Now, what you're trying to do with the regularizer, you're trying to minimize the sum. Let's say you have L2, you would have the sum of the Wit, Wj of t. Actually, you want to get it like this, times Wij squared. You're trying to minimize this over the lambda i's, big lambda I. The problem is that this is not convex because you have the lambda j in the denominator. So this is minimization, yeah, over the lambda i's. And to make a long story short, to bring out the convexity, because if it converges always to the same point, there has to be a convexity issues. What you have to do is make changes of variable. First, you write Mij is the ratio. So if you do that, this arrow function becomes strictly convex as long as p is greater than 1. But if p is less than 1, this doesn't work. So to make a long story short, you end up with this variable here being the log of the lambda I over lambda j. So if you write this minimization problem in terms of these guys, you're going to get minimization of a cost function, which has this form here, e to the Lij, Wij, because you have the square, so you're going to get this, okay, with respect to the Lij's. But then you have a big problem, which is the constraints on the Lij's, right? You have many more Lij's than lambda I and lambda j's. The arrow function is strictly strictly convex in the Lij's. That's clear because it's an exponential. These terms are positive. You're summing these. So it is strictly convex. So this part is clear. It's a nice, strictly convex function. The problem is, what is the constraint you have on the Lij's? If you give me the lambda i's, you can get the Lij's. But if you give me the Lij's, can you retrieve the lambda i's in a unique way? What is the constraint you have to put on the Lij's so that you can retrieve lambda i's in a unique way? And it requires some work to think about it, but the answer is extremely simple, actually. So if you think about it, suppose you have, let's say, 4 neurons like this. You have lambda 1, lambda 2, lambda 3, lambda 4. These are the scaling multipliers on the neurons after many, many, many scales. It's a product of all the little lambdas applied to each one of these neurons. And here you get a factor that's going to be lambda 2 over lambda 1. Here you have lambda 3 over lambda 2. And here you have lambda 4 over lambda 3. So if you take the product of these guys, of course, it cancels. You're just left with lambda 1 and lambda 4. So the product, if you go to logarithm, the product of the Lij, the sum of the Lij over a path like this has to be equal to the log of lambda 4 minus the log of lambda 1. So the log of the last one minus the log of the first, okay? So if you take a path from an input neuron to an output neuron, for input neurons and output neurons, the lambdas, little lambdas, are all equal to 1. You don't scale the input neurons and the output neuron. And so the big lambdas are equal to 1. So this guy is 0 for a path that goes from input to output. So you have sum of Lij has to be equal to 0 on every path that goes from an input unit to an output unit of the network, okay? And what kind of constraint is this? This is linear. So now you have a nice convex optimization problem, strictly convex objective function. And the space of constraint is the intersection of a bunch of hyperplanes, but they are all linear. So it's a linear manifold characterized by this. The sum of the Lij has to be 0 on any path going from an input neuron to an output neuron. So it gives this picture geometrically. That you have a nice ball like this. And below it, you have this hyperplane. So these are actually, this is the sum. It's this guy here. It's the sum of E2 Lij Wij squared, or if it was, you know, a P regularizer, you would get a P here with an absolute value and a P there. But that's the function that is strictly convex. This is the manifold, linear manifold of the Lij that are consistent with the multiplier. So it's a linear manifold. And when you do balancing, you're starting from a random point, which actually is always in this space corresponds to the origin, because at the beginning, when there is no scaling, all the lambdas are equal to 1. So all the logarithms are equal to 0. So you're starting from the origin, and then you have a random walk of balancing operation like this that ends up on this point here. So that's why no matter where you start, for a given set of W's, you always converge to the same balanced state. Thank you. Any questions?
First of questions. This is a naive question. So you would have to rescale the bias as well, is that right?
Yes, of course.
And is in regularization, is that usually what happens in the term, the L2 term? Does it have the biases, or is it just the, you could add it?
You could do either way, but I think it would be sensible to put the bias.
I see. And one advantage that I see of this, maybe, if I understand correctly, is that, you know, you could reduce the regularized, doing this versus, you know, doing gradient descent on the regularizers, you could reduce the value of the regularizer by just globally scaling all the weights by some value, which that doesn't have any computational significance. Whereas here, you don't, you know, globally scale the weights by a constant because it always converges.
If you globally scale the weights by a constant,
right,
you screw up the network.
Oh, really? Okay.
Your data prediction is destroyed.
Even in the, okay, I'll have to think about that. Yeah, thank you very much.
Well, are you implying that you can initialize the weight so that the regularizer is already at the optimum?
you can start from random weights before learning, and you could balance the network before learning, and then do gradient descent. You could definitely do that, and maybe it helps learning. You know,
so this could speed up the training.
Or you could alternate, you know, gradient descent and balancing. I mean, there's a lot of little things like this that you can think of. Yeah, Klaus.
So if you, and I haven't thought enough, maybe the question is trivial to answer. So if you balance and you look at the eigenvalues of the Hessian, what do you have less, you know, is the condition number getting better?
Maybe, I don't know.
Because that could be an interesting one.
I mean, no more than gradient descent. Again, gradient descent is going to balance things. So it's, you know.
Is there any relation with the fact that each neuron is a bottleneck when you propagate the gradient?
Not sure what
because in the sense that when you backpropagate the gradient, you multiply the partial gradient that is entering a neuron to all the weights. And so you have a common factor that is multiplying all entering weights.
When you do backpropagation, you don't have a common factor. I mean,
well, the neuron,
from each direction,
from the neuron, you have the partial derivative that is coming from top, and this is going to multiply all the weights, and then you also add the contribution of the output of each entering neuron, no? But there is a multiplier that is actually common to all the weights.
Well, the derivative of the ReLU is either 0 or 1, so when you backpropagate.
No, but you have the partial gradient that is coming from the top.
Yeah.
So you have a number.
But on each you know, on each outgoing weight, there is a different gradient coming in.
Yeah, I was just wondering if there is some relation to the fact that you have a common factor that is multiplying all the weights when you backpropagate.
I don't see that there is, you know, the same factor, but, you know, let's sit down and go through the numbers. No, this applies to skip connections. The skip connection is just an outgoing connection. It goes far up, but this doesn't have to be layered. It can even be a recurrent network. You could do balancing on a recurrent network. It has nothing to do with skip connections. There is a rejected New Reeves paper. And there is a paper going on archive in a few days.
So I think we can continue the discussions. Actually, we can continue the discussion offline. Thank you, Pierre, for the great talk.
Thank you.
I think there should be a lot more discussion later on.
Thank you very much for this workshop. So think of the previous two talks and then lower your expectations, because this is going to be different, the usual standard stuff. So my name is MT, and I'll talk about some of our work that we have done in the last 7 years here, the Bayesian learning rule. Just to start with what we have been interested in, what I've been interested in for many, many years is the question of adaptation. How can you make intelligent machines that can adapt quickly and continue to do so throughout its life? And it's similar to how kids learn, now people learn on day-to-day basis. They absorb new knowledge, update their, their brain, and live their life. But if you look at what happens in machine learning right now, if you have a small change in your model, GPT that's trained in 2021, it's not updated, and you want to update it, you have to again sort of resort to the same techniques, throw a huge amount of resources, money. So only few people like big tech and rich folks can train the model. It has a huge environmental cost. So this is not right, and we want to fix this, and we want to be able to apply the deep learning, models to more dynamic problems where things are changing on day-to-day basis, like during pandemic, or to understand climate change. We need methods where the knowledge can be updated over time, slowly, right? And I also believe that lots of harmful and dangerous things that are happening in AI can be fixed if we actually know what we are putting inside our model. We understand what it knows. We put a new data in the model, and we see the improvement. And if we do this slowly, somehow during training, then there's a hope that perhaps we can fix the mess that we have created in machine learning now. So that's kind of what we want to work on, and we have been going towards this. One of the motto that we came up with is retrain less and reuse more. So okay, so I will just talk about like some few things. So I guess I have until 12:15. Okay. I have very little time. So I'll just kind of give a very short summary of the work. So details I would not be able to convey. I hope I don't get carried away too much. But the first thing that I'll show is how, all this Bayesian stuff that we feel like doesn't really work very well, somehow this can actually help. So I'll talk about Bayesian learning rule that bridges the deep learning and the Bayesian learning, these two different paradigms of learning. And by doing that, we are somehow able to bring, train big models by using Bayesian methods that people consider is not possible. So this is quite exciting for us. But we're not just doing this because it's good to be Bayesian, but we are also trying to show that if you're actually able to train, use these, Bayesian methods, you're able to improve other aspects of deep learning. So I'll try to talk about very briefly about calibration and like understanding the model, so the memory of the model, and then how to use that memory to add new data that may be new or old. So to do lifelong learning, for example. Ultimately, this is what we want. We want human-like quick adaptation. We're not there yet, but we're on a very good path, and I just want to give you a snapshot of where we are right now. So there are 7 papers I've listed here. Slides are on my webpage, by the way. You can go and check it. The first one is it's the main work, but everything else is kind of a consequence of it. So by just having this one Bayesian learning rule, we're able to do lots of things. And that's the point, the takeaway of the talk. Okay, so stop me anytime and ask questions. It's just that you will be delayed for lunch, so that's fine with me. Okay, so start with the Bayesian learning rule, right? So in deep learning, often we minimize loss, like some kind of training loss with some regularizer. And well, we don't really do that actually. We say that we're doing it, but we early stop. We do a lot of, thorough regularization. So my whole, line of work that I'm creating here is about not doing this, but doing something else, which is Bayesian. And this is something like evidence lower bound. So what people do in variational inference, like in VAE. But if it doesn't look very familiar to you, don't have to worry about this. Basically, just think of it as like instead of learning a theta, which is the parameter of the neural network, you are learning a distribution over it. And you're going to force it to be something quite simple, like an exponential family. Just think Gaussian for today. So just going to do Gaussian approximation. And there's an entropy regularized. I don't know if it's optimal transport, but somehow something is similar. But I'm basically saying we shouldn't be doing this, we should be doing this. And even when we are doing this, it turns out that actually we are doing this. So that's what we tried to show, that somehow there's a unifying view of machine learning, that if you see that algorithms optimizing this somehow recover algorithms optimizing this if you make some crude approximation. Okay. So that brings me to this natural gradient descent algorithm that I call Bayesian learning rule. But it's quite simple. You have natural parameter of the exponential family. So it's, let's say, Gaussian, then it's somehow related to the mean and the covariance. And you're simply taking the gradient with respect to that and scaling it by Fisher. Okay, so it's quite straightforward. And basically the claim is that if you do this, then this update equation, so don't have to know the detail, but it's a natural gradient descent updating some parameter of the distribution and operating on a different objective. So if you do this learning rule, then you can do a lot of things with it. That's the point. Okay. So you could change the posterior approximations here, or you can make some approximation to the natural gradient descent, and you can show that this reduces to the algorithms that people use to optimize this. Okay. And then you can do perturbation on the posterior distribution Q, and that will help you to understand the memory of the model. And then you can use the memory to do lifelong learning. That's kind of the path. Okay. So so maybe next I will just maybe give the big picture thing. So if you go in the main paper, you'll see this table, and essentially it shows how the Bayesian learning rule unifies many learning algorithms. So essentially you have to, so there's a list of algorithms here, and they're from optimization, from deep learning, many textbook examples that you read in Bishop's book, for example. But you basically just choose different different posterior approximations. So they're like exponential family or mixtures of exponential family, but basically those are the ones that you choose, and you get different algorithms. You have to make some approximation to the gradient, because if you don't want to minimize the expectation of the loss, you have to somehow be ignore the expectation. So it's something called delta method that you employ, and then you can get all of these things. So of course, this looks quite good, and then when we present it to, many years ago when I was presenting it to people, they say, oh, everything can be approximated by everything, and it's all fine, it's not useful. But we spent many years to see that if we, relax these approximations, somehow it gives us something better. So it's trying to improve deep learning by understanding these approximations, relaxing them. So that took many years, and now this is really just this year actually, but we've been working on this for almost 7 years. So when I actually joined here, I wrote the first paper like the month that I joined here in 2016, and it was accepted next year. And I thought, well, I'm going to be famous, but didn't happen. But yes. So, but that was actually as good as I thought at the time. So many years later, it's very nice to see now that we can, we have large models, so we can actually train them. So we have this method called I1. And essentially what I'm showing you here is the GPT true training. It's quite large model and large data. And the red one is I1. And it kind of looks like that it's a little bit slower in the beginning, but it gives better performance in the end by some extent that NLP people tell me that it's good. So I'm happy with that. And this going slow is not a problem. You can actually tune learning rates, and you can make it more aggressive. But if you're more aggressive in the beginning, then you pay in the end. So there's some trade-off, and you need to do some tuning. So we can really take this natural gradient descent algorithm, right? It looks very fancy and theoretical, and we can, without many approximation, actually without any approximation, let me say, you can get to this. Okay, so how does this happen? Actually, it's quite nice if you know RMS prof in deep learning, or if you don't know it, it's still fine. You compute like mini-batch gradients, and then you basically take steps in that direction, and you rescale your gradient by some kind of Hessian estimate, but it's not Hessian. People don't like that, so they just do simple square of the gradient, right? And that's RMS prof. Now, if you take the Bayesian learning rule, right, it's information geometric natural gradient descent algorithm, and you use Gaussian approximation. So that's the only approximation you do. You make this choice, and then you just do clean math. It's very, very clean. There's no more funny business going on there. You get line by line correspondence between things, okay? And I don't have time because I'm hungry. So I'm not going to go into the detail of this, but really like the small details, like you have to perturb because you're computing like the expectation of the loss. So you sample from a Gaussian, and then you don't do square of the gradient, but you compute a Hessian estimate. This is reparameterization technique. So it's not it's a Monte Carlo approximation. So you have to do that because otherwise it's not practical. So you do a reparameterization trick, and then you add something to make sure that Hessian never goes negative. This is from Riemannian gradient descent, by the way. But it's a proper Newton method that doesn't do square roots over H. So it's a Newton method. It's online because you do moving averages like in RMS-prop, and it's variational because it's Bayesian, and it's improved because of actually this term. Okay, so you can look at this blog. I just published it like last week, and there's not much. You can go and download the code and change like 2 lines, like just remove this Adam optimizer and replace it by I1. And if you want to add more samples, you can add like not one sample, more samples if you want. But that's it, and then you can run this. So I mean, it took many years, but like we've been like kind of making constant progress over the years. So like the first paper for deep learning was written after I wrote the AI stats paper in 2018 in ICML. Then we improved it further, and then the next year we had to kind of deal with Hessians going negative, and that took a while for us to get it right. But once that was right, the next year we, some of the folks in the group, they applied this to NeurIPS challenge, and then it got first prize. It was quite nice. And now we can do all sorts of things. We can run this on ImageNet, for example, and you get marginal improvements over SGD. But the nice thing is that, so you can see this, right? The times are almost the same. But if you look at the calibrations, they're much nicer because you're doing this kind of perturbation, and you're learning a distribution that helps you to align things a little bit better. Okay. So being close to the diagonal is better, and red is I1, and this one is Adam W. So it's only kind of corrected when the probabilities are extreme. Sorry? No, not yet. I don't know. Yes. So hopefully some statisticians will do that, but we have been busy in making it work right now. Yeah. So another nice thing is that it doesn't overfit like Adam W. So Adam W and I1 are almost the same algorithm, line by line, right? But if you run Adam W for a very long time, it starts to overfit on image classification. It's a very well-known problem, and it doesn't actually beat SGD. And SGD is a simpler method, so you should be able to do that, but it starts to overfit. But here we kind of solve this problem with I1. It doesn't have that issue. So you can run it really, really long. You don't have to do early stopping or anything. It just kind of finds a stable place. So yeah, we've done this line of work, and it's just, stories kind of get repetitive. It's the same thing. If you want to do adversarial perturbation methods, so this is SAM. It's, they also do something simple, actually, like they will draw a circle around where you are during training, and then you look at the kind of worst case loss. And it looks like, you have a Gaussian somehow because it's a circle, right? So you think that you're somehow doing something non-local, and you can actually really connect it to Bayes. So if you did Bayes with Gaussian, your expected loss, you can kind of rewrite this as a noisy, thing. So they look very similar. But actually, you can show with this BLR style of thing that if you actually did the right parameterization, so sorry, lots of details here. But the very simple version is that if you do a optimal convex relaxation of this by Fenchel biconjugate using a Bayesian interpretation, then you can show that this is kind of the same. So you can again, run an Adam-like optimizer for SAM, and you can learn variances, and you do the same trick. So it all works, nothing breaks. Okay, so it shows that I've used 16 minutes, but in reality, I have 10 minutes more. Okay. Okay, so, okay, yes, good. So this is the first part, to show that we can unify all the algorithms, we can improve some calibration, some aspects of it, we can train them, run them, all of this stuff, right? Great. But this is not the original goal that we had. We actually really want to do adaptation. So we want to, like my favorite way to show what's, so we have a big system, we want to somehow add something to it or remove something from it. So we just want to change the system, adopt the things that are inside the system. And how can we do that? So, well, one of the fundamental ways to think about this is perturbation and sensitivity, right? So you would go in somewhere and you will, wiggle some parts of the system, and if it really affects the performance or the behavior of the system, then you know that that part is important, right? So is basically measuring sensitivity to certain perturbation, and these ideas are rooted in duality. Big words, but what I'm actually trying to say that once you have this Bayesian learning rule, you can essentially do all of these things by just running the same algorithm. Sounds magical and sounds like I'm making it up, and I thought that many years ago, but been working on this for 4 years now. And it's quite nice, actually. So the idea is actually very, very simple. You can perturb the system using the posterior, because posterior has all the knowledge in it. So that seems like a very intuitive thought, but would it materialize in a more computationally easy way? It turns out it's quite nice. Again, thanks to exponential family. So in the Bayesian world, this is a very old idea. If you want to change something in the model, you can simply just kind of remove the contribution of a part of the model. So let's say you want to remove a data point, then you can simply divide by that likelihood. So here I've written this with likelihood minus, that I'm trying to remove it. I can simply just divide it, and that simple operation ensures that that term is gone, that data is gone. I'll have to renormalize it, which is an expensive operation. But if you are in exponential family space, then it's very easy, because normalizing constants are known. So dividing, it means subtraction. So how do we apply this to non-exponential family cases, right? Neural network, they're not exponential family, not convex cases. So it's actually quite nice, and this is what we've been working on. With Bayesian learning rule, essentially you can do this on anything by taking steps of natural gradient descent. So essentially you just look at the expectation, sorry, this should be log likelihood, but it's the same algorithm as before, and I have removed the Fisher and I've put this tilde to say that this is a natural gradient, okay? But essentially what you do is you take log of this, okay, and you run natural gradient descent on it. So log Q minus log, so you're subtracting this guy. So somehow adaptation of knowledge becomes addition and subtraction in the log space, and you do natural gradient descent. It's very beautiful. Sometimes people call it task arithmetic these days, but it's an arithmetic, it's a Bayesian arithmetic in that sense. The main point of the work is to add this correction term that actually solves a really old problem from this filtering times, but I'm not going to go into the detail because, again, we're running out of time. But I will not talk about these details now, and but I will just show you the consequences of this. So essentially, to remove an example, you just run a step of natural gradient descent, and it's basically you take a step of I1 algorithm. And if you do that, then you can see how much the model changes. Okay, so you would take a step of I1, and based on that, you'll see how big that step was. If the step is big, then the if you want to remove this data example, then the model is going to change a lot. So this is the perturbation, is the removal of the example, and you're measuring the sensitivity through natural gradient descent. And on MNIST, if you do this, it looks quite nice. So like all the zeros here for low sensitivities are very regular, but high sensitivities are all kind of weirdos, you know. So there's some like mislabeled example or ambiguous example. So like this is, we don't know what it is, right? It's supposed to be 3, and this is a weird guy. So this guy is more, this side is more interesting. So you can see that basically this is extending the support vector machine, kind of like, you know, the idea of support vectors or the boundary through this Bayesian ideas, where we don't have to talk about convexity at all. There's no need to stop, you know, because it's not convex. You can still just apply these natural gradient descent and do it. So yeah, we've been kind of doing this, trying to understand. So we have a paper on memory perturbation equation, which you can look at the details of all of this. But essentially, you have a trajectory, and you want to figure out what points in the trajectory really are essential for the behavior of the model. So you have a GPT that you're training, and then you know that you're adding New York Times data in it, and then you have to see how important is this? Am I okay if I get lawsuit by those people? You should be asking that question when you're training the model, right? But there are no tools to do this. Basically, this is what is giving us that tool. So we want to understand, if I change something, it goes somewhere else. Well, yeah, where does it go? If I have to do this, then by removing the thing and retraining, it's a lot of work. So I just want to estimate it, right? And basically, that's what's happening. You use the BLR, then essentially you can kind of recover all the ways that people do right now in deep learning. And I'm not going to go into the detail, but if you look into the one step of I1, essentially you can write that step in terms of like sensitivity as like prediction error times prediction variance. I don't have time, so I'm going to skip this. But it's very simple. There was a poster yesterday. Talked to some folks here. They'll tell you, okay. I'm just going to skip all of this. You can look inside the memory of the model and, you know, split the error a little bit more. You can, you know, data scientists can use this and kind of analyze what's happening inside the model by just looking into these maps. But most importantly is that we are able to answer this kind of what if question. You know, what if I remove this data during training from my model? What if I add this data? What would happen? And if you actually did brute force training, which is on x-axis, you'll get some performance. And that matches very closely with, like, you compute these estimates using I1. You take just take a step of I1. You compute an estimate of how much the model is going to change. It correlates quite well. Okay. I hope that this. You can also do this on like really fine-tuning large language model. We have a paper on this year. It's kind of same story. Like they all, you know, the brute force one aligns with what we estimate. And estimation is based on only like, you know, your current model. You don't have to retrain these things. It's quite nice. Okay, so I'll just take 2 more minutes and I'll finish. So it's actually quite simple idea now. Like you want to do continual learning, like lifelong learning. You want to add data, then you would multiply, right, instead of removing things. And you know the answer. If you multiply, then you just add. So this sign becomes plus. Okay, and then you do the same thing. So we did this actually, originally we did more complicated things. So we did this work in 2020, but we didn't know why it was working well. And this is how we come out to discover all these things. But at the time, we actually showed that if you know, you figure out these high sensitive points and you freeze them. So this is like memory. And then when the next set of data comes, you have to retrain on this, and then only this memorable past is what I called it at that time, right? So you're somehow trying to preserve, you're replaying some gradients from the old times. But it's essentially, you know, those terms that I showed you in that Bayesian learning rule framework. Okay, so it worked quite well. You can do lots of stuff with this. You can combine lots of different methods that people have. functional regularization, replay methods, weight regularization, all of these, they kind of pop out of those terms in red that I showed in the previous slide. So they're all kind of ways to somehow, do these natural gradient descent, which is quite nice. So one of our goal for next 1 or 2 years is to really do this at large scale. So we've got somewhere now, like, so sorry, maybe the most important. So this is my last slide. Basically, this is on ImageNet, so higher is better. And if you train on joint, like you give me all the data at once, I get this kind of performance. And I basically want to get there sequentially by seeing like few classes at a time. And we got here now. So what I'm actually increasing in the x-axis, I'm increasing the memory size. So if I just use maybe like 10%, it's actually 7.5% of the data in ImageNet, I can almost reach 80% of the performance. So I'm very close. Our goal is to kind of push this up and reduce the memory size. So hopefully we'll be able to converge like this in near future. But I'm very confident that this will happen. Okay, so just summarize in 10 seconds. I showed you the Bayesian learning rule that bridges the gap between deep learning and Bayesian learning and many other unifying learning algorithms. It runs quite well. You can download the code and run it. It improves certain aspects of deep learning like calibration, uncertainty, memory, and something else, lifelong learning, and you can understand and fix model behavior with that. We have a project called Bayes Duality Project. We are very lucky to have this funding and have collaborators that have been working on this. There's like almost 30 people working on this. But I should actually take this opportunity to thank you, Amari Sensei. So he was here in 2018 and spent some time talking to the interns. And I've only used the second chapter of your 2016 book. So that was enough to do all this. So thanks a lot for being here and for your work that you have done. This has been very, very useful. And okay, I mean, yeah. So we've been working on Bayes duality. We have a workshop. If you have some students who wants to attend this, please send them. I mean, we're not able to provide funds this year, but hopefully next year we'll figure some funding schemes. But we're doing lots of big things with Bayes duality. But if you look into Amari Sensei's book, he also introduces a Bayes duality in his book, and I didn't know about this before coming up with the term about Bayes duality. So it's a very amazing coincidence that we are rediscovering things that Amari Sensei has already done them before. Okay, with that, I'm done with the talk. Thanks for listening.
Thank you, MD, for the great talk. Any questions from the audience?
Thanks for the interesting talk. I'm curious how similar or different is this perturbation memory equation to the influence functions you have in robust statistics. That also allows you to adapt for change in distribution by removing or adding.
Yeah, so I will really encourage you to read the paper because actually it is bigger than it. Okay, so influence function is a special instance of memory perturbation equation. So I've written it there actually. So you could see that you could derive it from it. But you can do more with the MPE. It's quite fun.
And one more question. For the Irvine algorithm, how often do you sample from this Gaussian?
Because we do one sample right now.
Just one throughout training?
No, one at every iteration.
But that might add to the wall clock time, right? A bit.
Yeah, it does.
At large scale, it would maybe.
Not really, but it does a little bit. Okay. So if you maybe you can see it, right? So you see a little bit of gap, right? This 12 hours, that gap is the sampling. But at ImageNet scale, you see like almost no difference. So yeah, I mean, I think this is necessary. It should be done. Without it, it's not very good, the uncertainty. So on ImageNet, it's negligible. So it's okay. It's not that bad.
Other questions?
All right, everybody wants lunch. Let's eat.
So let's thank Andy again.